Hello, everybody. Welcome back to our next topic in grade 12 U Physics. Today we're going to be focusing on some projectiles. And you've done projectiles in grade 11 physics, so it's just a matter of building on that. And we're actually going to look at solving some of these equations in general. So again, if you're solving just a simple projectile problem like in grade 11, you check out some numbers and you come up with a flight time or maximum height. But all the work that you did would have to be redone for a problem with even one number difference. So our goal today is to come up with a sort of a general strategy or a general equation of motion that describes how a projectile behaves and use that to make our lives easier. Before we get too far into it, just a quick review of projectiles. So remember that a projectile is any object that is traveling, and the only thing affecting it is going to be gravity. So again, this is often cases of like balls or people jumping out of planes or rockets once they've already turned off their rocket boosters. And so remember also that the nice thing about projectiles is that they follow a nice parabolic arc. And the reason they do that is because of a nice thing that we can actually observe is that a projectile once it's launched, its only influence is gravity, and so then it's accelerating down at g 9.8 meters per second squared, and there is no horizontal acceleration. And this is pretty key. So that means that whatever speed the projectile left with in the horizontal direction, it will always have until it's no longer a projectile. Remember, again, a projectile is an object that is not affected by air resistance or any other forces. So once it hits the ground or the wind blows it, then it's no longer a projectile. And again, just one more thing to point out before we go, that on Earth, nothing really will be a true projectile, but lots of things will become close. And so as long as we're not talking about giant objects with lots of air resistance traveling very fast or very long, it's often safe for us to ignore air resistance, or at the very least, if we ignore it, we can get an order of magnitude answer for where something will land or how long it will be in the air. So again, projectile follows this nice parabolic arc. And over here you can see the stroboscopic view of two different balls falling at the same time. The yellow one was launched with a horizontal velocity, and the red ball was dropped with no initial velocity. And all the way down, they're completely in line with each other. The only difference is the yellow ball is moving off to the side at the same time it is falling down, and the red ball is falling straight down. So our general strategy here, again, as his last point says, is we're going to be looking at breaking these motions into horizontal and vertical components. The thing that will happen to common is the time, because again, the ball can only be at one place at one time. All right, so if we look at a common projectile, leaving with some sort of initial velocity, and here I've called it VI. So this would be the velocity it's leaving at, and here I've drawn a representative vector. The first thing we always want to do is break up this velocity into horizontal and vertical components. Again, a reason for that is because each component we can deal with separately, but we don't know much about this initial velocity at whatever angle it's at. So we have to break it up into so much over and so much up. And again, hopefully you can follow from simple trig ratios, because notice again, this is a right angle triangle, that our initial horizontal velocity, so I've called it Vix, is just given by Vi cos theta, and the initial vertical velocity is just given by Vi sine theta. So that's again just simple trig ratios. So looking at these in a little more detail, the one thing again that I mentioned on the last page is that for all projectiles, the horizontal velocity is constant, which means if we know the initial horizontal velocity, we know that the horizontal velocity is the same everywhere along that flight. And for the vertical velocity, of course, it changes because gravity is causing acceleration. And so if we go back to our kinematics equations, we can actually pick one out that's going to help us here. And so this, believe it or not, is actually one of the kinematic equations that I showed you the other day, but it's just in a bit of a different form. So notice this Vi sine theta is just an expression for the the initial vertical velocity. So we can read this then as Vf equals Vi minus this other value over here, which I've written as G delta T. And so again, this is that same kinematic equation, our defining equation for acceleration, given by this, just rearranged, and some of the terms are expressed in terms of the projectile language. The reason we have G here is because G, of course, is the acceleration caused by gravity. Another thing you might be noticing is if you work this out on your own, it looks like this should be a positive sign as opposed to a minus sign. And hopefully if you think about it for a second, you can realize that it has to do with this acceleration. Again, the acceleration from a projectile is caused only by gravity, and so this g will actually be pointing down. So the one thing I maybe should mention here that when we're using g here, we don't have to worry about putting in 9.8 meters per second squared down or negative 9.8. We just can just leave g as plain old 9.8 because the minus sign is taking care of it for us right there. So there's our kind of initial velocity, or sorry, final velocity expressed in one way. Here is the final velocity expressed in another way. And the second way here, this would be using another kinematic equation. This would be using K5. So notice it gives you the same thing, but it doesn't involve time. So there's different ways to get at the same idea. And our last expression I have here, this is just K4, again expressed in the terms we're using for projectiles here. So here's our v1, and here's our acceleration term. And this expression will tell us the distance in the y direction this object has traveled after any time t. So notice for any given problem, vi sine theta would be a constant. So only thing varying over here would be delta t, and putting in whatever delta t you want will tell you where vertically this object is, so how far up or down it is from where it started. So these are again our sort of guiding principles. With that in mind, let's take a look at an example here. So here's a golfer. They're standing at the top of a hill, and it's 14 meters above where the ball lands. So maybe they're teeing off and shooting towards the green. And it's leaving with initial velocity of 25 meters per second at an angle of 30 degrees above the horizontal. So over here on the right-hand side, I've got a nice little picture for you. So here is the initial velocity. And notice, again, I've broken it up into horizontal and vertical components. So VIX and VIY, and here is that 30 degrees. The dashed line here represents the particle motion, in this case the golf ball motion. I notice it is a parabola again, and that's because it's a projectile, and so the only forces acting on it are gravity, causing an acceleration of down. So notice the VIX is now just Vx, and it is a constant horizontal component the entire way down. But what happens to the vertical velocity is it starts off very high up, it gets smaller up for a split second here, right at maximum height, it goes to 0, and then the vertical velocity starts increasing downwards. And the darker green arrow on your screen, that's going to be the recombined velocity, so the horizontal and vertical components added together again. So here's our sort of situation, and the golf ball, of course, lands over here. So this distance here is 14 meters. And I want to know a couple things here. I want to know what is the maximum height of this golf ball, so how high up in the air does it get, and the ball's velocity on landing. The one thing that I maybe should have made clear here, we can assume that it's a projectile and it has no air resistance. If you've ever played golf, you know that's probably not the best assumption sometimes. Anytime you have a hook or a slice and the ball curves left or right, that's certainly a huge effect of air resistance and drag. But let's just try and ignore that for right now and just deal with it as a straight projectile. So we do want the maximum height, so we want to kind of know what is this delta dy. And so I'm going to be using this expression, which is again just a rearranged form of, or sorry, a recasted form of K5. And we want delta dy. We want to know how high it is up. We know the initial velocity. We can find that using VI sine theta again, going back to our picture here. So we know the initial velocity is VI sine theta. We know that g, of course, is 9.8. We know we're looking for delta dy. So what the heck is VFY? What is that final vertical velocity or final y velocity? And again, one more time, that we're looking for the point where the ball is at its maximum height, which means this point right here. And the key point for this problem, again, is that at this point, the vertical velocity is 0. So we sub in 0 for this point, or for, pardon me, this velocity. We rearrange our equation, plug in a couple numbers, and I'm going to leave that to you, but hopefully come up with a maximum height of 8 meters. So let's just pause for a second here and think about this. We found that our maximum height is 8 meters. But if we look over here, the golf ball is leaving 14 meters above anyway. So how does the 8 meters factor in? Did we make a mistake? And no. Remember, your kinematic equations, I believe I said this in grade 11, and I'll say it again. Your kinematic equations are stupid. They only know what you tell them. And so if you don't tell them the correct things, they'll give out the incorrect answers. So notice we told the equation where to start actually counting by giving it an initial velocity. We said compared with this velocity, where is this golf ball now when we have a final velocity of 0? So that means this equation will be comparing everything to this point because that is where the initial velocity was given by what we said. So what this means is then this distance here is actually the 8 meters we found. So just something to be cognizant of when you're solving these problems of where reference points are. And so another way to say that is this golf ball is actually 22 meters above where it lands, but it did gain 8 meters from where it started. So there's the maximum height of the golf ball. Hope that's okay. And the next thing on our list is determine the ball's velocity on landing. So I really want to know this vector here. Half of the work's already done for us. We know Vx. We know that's a constant value. It won't change. So really we're left with Vy. That's kind of what we need to find. We want to know the final vertical velocity. Notice it won't be 0 because we're not dealing about max height. We're dealing about when it lands. So we have to redo another calculation, which we're going to start here, and find the final vertical velocity. So if I look down here and see what we've done, here's our expression for K5. Notice the same one is up here. But again, we're dealing with this as our initial and this as our final, as opposed to this as initial and this is our final. So with that in mind, we're looking for Vfy. We know initial velocity, again, is the same as it was before. And for delta dy, notice we're going to put in the negative 14 meters. And the reason we're doing that is because from here to here, this golf ball has changed its vertical position by 14 meters. And so that's why we're going to put in this 14 meters here. And again, negative because it's going down, it's decreasing in height. So again, I trust you can calculate for until you're blue in the face, and you come up with plus or minus 20.8 meters per second. And normally, again, I imagine in math class, you're like, okay, well, if we always just told to ignore the negative root, because generally it's not the one you want, and that's certainly true. And we do want we normally don't want the negative value, but we want to look at what these values actually mean, because they do have a lot of relevance. The plus and the minus both have some physical significance, and I want you to think about this. Again, your equations don't really know what the heck what they're doing. They just do what you tell them to, much like your calculator does. And so it's saying, well, the final velocity when the height is changed by 14 meters is either up at 28 meters a second or down at 28 meters per second. Hopefully from your common sense, you can realize that we want the down version, but the up version, again, does have meaning. What it means in this case is if we trace this parabola back, so it was now 14 meters below where it started, this is the velocity it would have needed to have the velocity you told it right here. So hopefully that makes sense. I wouldn't be too concerned about it if you're confused, but do ask me tomorrow in class if you're still confused about it. But we do want the negative value of 20.8 because we want the down version, which is over here. So now we know the vertical velocity. We know the horizontal velocity because it's constant. So to find the final velocity, it's just, of course, Pythagorean theorem. And we come up with our final velocity magnitude of 30.1 meters a second. But all vectors need to have a magnitude and a direction, so then we have to find the angle. And again, it's just some simple trig. We know the vertical velocity, we know the horizontal velocity, do some rearranging, and you should come up with this value here, 30.1 meters per second, 44 degrees below the horizontal. So it's, again, hopefully a straightforward calculation for you there. So far this has all just been grade 11 repeated, but with some different terms and maybe a different sort of strategy with things in general as opposed to plugging in numbers right away. But I do want to keep things moving along here. And so I'll give you a chance to do a little bit of practice using some of the new terms we just talked about. Notice the answers are here for you. So what I'm going to suggest you do is you pause the video for a few minutes, you try these questions, and you make sure you come up with these answers. And of course, if you don't, that should be the first thing we talk about in class next time I see you. So I'm going to assume now that you've solved this problem correctly. Everybody's happy, and there's one other thing I want to talk about, and it's becoming even more general. So one of the real powers of keeping things in general is you can solve a lot of problems um, with very little work if you've done enough up front. So what I've done here, and I'll walk you through these in just a second, is I've solved the flight time, the range, and the maximum height for any projectile in any situation, so long as the vertical displacement is zero. And what I mean by that is that this object, this projectile, is leaving and landing at the same height. So nothing going off a cliff, nothing being thrown up to a balcony. These would only be things that start and end at the same spot. So if you want to think in math terms, that's a parabola with um, the intercepts being where we want. So this would be the launch position. This would be the landing position. So for any projectile you could imagine, with this scenario where we're having zero vertical displacement, I have now solved for you, you're welcome, the flight time, the range, and the maximum height. It's just a matter of shoving some numbers in. So I'll skip to the end and then I'll come back and fill in the blanks of how we did this. But there's your flight time equation, there's your range equation, and there's your maximum height equation. Um, and really, it's not terribly difficult how I did this, so let me walk you through what we did. So for flight time, I started with the K4 that you saw before. And notice again, you plunk it anytime you want, and you get the vertical height, or vice versa. If we plunk in any vertical height, we can solve it for the time. And so if we have zero vertical displacement starting in the same spot, delta dy is just simply zero. So delta dy goes to zero. And so we're solving this expression here. So two ways you can kind of go about this. Well, probably more. You learned a bunch in grade 10 math how to solve a problem like this, but I think the easiest that I would do is factoring. And remember, what this says is I have a number multiplied by another number and I get zero. The only possible way that can happen is if one or both of these numbers is zero. So one option is delta t equals zero, and the other option is this equals zero. And they're both, again, equally valid. They both mean something very relevant. The first one, delta t equals zero, is the initial flight, or sorry, the initial launch. Because again, you've told your equation, find me a time where here's the initial velocity, here's the acceleration, and it hasn't gone anywhere. The equation spits out, well, obviously, before it's gone anywhere, so time equals zero. But the other less obvious one is going to be over here when it actually lands. And this would be the second option. It's one of the brackets. So if we just take this expression, set it equal to zero, and we solve it for delta t, we come up with this expression. So this, again, will tell you for any projectile in the entire universe, if I give it a g, a vi, and a theta that it's launched at, how long that projectile will be in the air for. Great, so that's pretty easy and straightforward. We're going to take this value and use it now in our range equation. And again, range is the horizontal distance that this projectile travels. So remember, this is just k1 for constant acceleration, or even k4 if you want, and just there is no acceleration. So we take delta dx equals vi, delta t. We know that vi is, oh, actually, that should probably be vix. Vix cos theta, or sorry, Vix delta t, so that means Vix is just Vi cos theta. And this is our expression for flight time that we just found down here. Notice, even though we're switching between vertical and horizontal components, that time is the linking factor connecting those two components together. So we can sub that in there. We arrange, we get this, and this looks kind of messy and ugly, so we can use one of those trig ratios, or sorry, trig identities, which I believe you cover in grade 11 math. But if not, don't freak out. If you need a trig identity, I'll give it to you. But we replace 2 sine theta cos theta with sine 2 theta, and they come up with a pretty simple looking expression for the range of a projectile. Notice no quadratic equation required. So there's the range of a projectile. Again, any one valid for any zero vertical displacement. And the last one I want to talk about here is max heights. So again, starting from this expression, this rearranged form of K2. Again, for max height, I want to find a spot where the vertical velocity goes to zero. So do some little bit of rearranging. I get delta t is vi sine theta over g. So that tells me at this time, the projectile will be at maximum height. So that is when I will find it at maximum height. So what I can do to find out where it will be then is take this value for t and plug it in for our vertical height equation. Notice I put max here. And again, max because this is only valid now for this time, and this time is only valid for vertical velocity of 0. So you just shove in delta t for these two, do some algebraic manipulation. Again, not too terribly difficult, so I can leave that for you, I think. But you come up with this, again, seemingly simple expression. So I think that's saves you a ton of work. You can find the flight time, the range, and max height for any projectile launched with 0 vertical displacement, and I've done most of the work for you. So that's it for today. Again, as always, let me know if you have any problems in class, and we will be using some of this stuff in class next time I see you. Have a great night.